Right now, the ground beneath you is racing faster than any airliner at the equator. Earth is circling the Sun at about 67,000 miles per hour, and the entire solar system is drifting around the Milky Way in a journey that takes hundreds of millions of years. Yet everything feels still. That is the quiet strangeness at the center of this video space is full of spin, from planets and stars to galaxies, neutron stars, black holes, and even the hidden angular momentum inside matter itself. If this calm science journey feels worth supporting, a like, a subscription, or sharing it with someone who enjoys slow cosmic mysteries helps boring Space Sleepy continue making thoughtful space stories. Thank you for spending your time here with this video. Leave a comment with the city or country you're watching from, what time it is there, and whether this is for sleep, study, or a quiet moment. Now the motion beneath stillness begins to reveal itself. At the surface of Earth, stillness is only local. A stone on the ground, a tree beside a road, a room with closed windows, and a sleeping body all appear motionless because they share the same motion. The planet turns beneath the sky once each day, carrying oceans, continents, atmosphere, and living things around its axis. Near the equator, that rotation moves the ground at more than 1,000 miles per hour. Yet the motion leaves no steady sensation because the air and surface move together. Nothing nearby offers a fixed background against which the rotation can be felt directly. The first clear sign comes from something farther away. Over a night, stars appear to cross the sky in wide arcs. The sun rises, climbs, and sets. Shadows shift. The pattern is so familiar that it feels like a property of the sky, but the larger cause is the turning of Earth itself. The motion is not an added detail to life on the planet. It organizes the rhythm of every day, controls the cycle of light and darkness, shapes winds, influences ocean currents, and helps define the climate system that makes the surface recognizable. This is the first layer of a much larger pattern. Earth rotates, but it also travels around the Sun at roughly 67,000 miles per hour. That orbital motion is not noticed in ordinary life for the same reason Earth's spin is not noticed. The motion is shared by everything bound to the planet, and the orbit is smooth enough that there is no simple inward feeling of speed. The surface seems steady because the frame of reference is steady. A person standing on Earth is moving with Earth, surrounded by air that moves with Earth, under a sky whose apparent motion is produced by Earth's own rotation. What feels fixed is only fixed within a moving system. The Sun adds another layer. It is not resting at the center of a motionless cosmic stage. It rotates, and it carries the planets, moons, asteroids, comets, and dust of the solar system around the center of the Milky Way. The solar system moves through the galaxy at hundreds of thousands of miles per hour, completing one circuit over a span of roughly 225 million years. That period is sometimes called a galactic year, though the name can make the motion sound simpler than it is. The Sun does not move through an empty track like a bead on a wire. It follows the gravitational structure of the galaxy, influenced by the mass of stars, gas, dust, and dark matter spread through the Milky Way. Its path is part of a broad rotating system, a disk in which stars and clouds move around a dense central region. The galaxy itself is also not a still island. It moves within the local group, a small collection of galaxies bound by gravity, and that group participates in the larger motions of the cosmic web. At each scale, another frame of reference appears. A room is steady relative to Earth. Earth is in orbit around the Sun. The Sun moves around the galaxy. The galaxy moves with neighboring galaxies through larger structures. None of these motions cancels the others from existence. They overlap. The result is not a simple journey in one direction, but a layered motion through space, with rotation and orbit appearing again and again wherever gravity has gathered matter into structure. This makes the ordinary idea of standing still difficult to defend beyond a local meaning. In physics, motion is always described relative to something else. A train passenger can sit quietly in a seat while moving rapidly relative to the ground outside. Earth works the same way, only on a far greater scale. The surface may feel unmoving because nearby objects share the same rotation, but relative to the moon, the sun, the stars, and the galaxy, that surface is never at rest. Stillness is not false, it is limited. It belongs to a chosen frame of reference. The deeper question is why so many of those frames contain turning motion at all. The pattern is not confined to planets. The moon rotates once for every orbit around Earth, keeping the same face generally turned toward the planet. The sun rotates, though not as a single solid body, because gas near its equator turns faster than gas near its poles. Jupiter spins so quickly that its day lasts less than half an Earth day, and its rapid rotation helps stretch the planet into a slightly flattened shape. Saturn, Uranus, and Neptune spin as well. Asteroids tumble, comets rotate as sunlight warms them unevenly, and gas jets push against their surfaces. Beyond the solar system, young stars form inside rotating disks of gas and dust. Mature stars keep turning long after their birth. Galaxies often take the shape of disks because matter inside them carries orbital motion around a center. Even galaxy clusters, where the pattern is slower and harder to measure, can show signs of rotation in the motions of their member galaxies and surrounding gas. Rotation is not decoration added to cosmic objects after they form. It is one of the main ways matter avoids falling directly inward under gravity. Without angular motion, many structures would collapse more simply and more violently toward their centers. With angular motion, collapse changes shape. Matter circles, spreads, flattens, gathers, and sometimes settles into long-lived systems. This is why rotation feels so common in astronomy. Gravity pulls matter together, but matter rarely approaches that inward pull from perfect stillness. It begins with motion, however small. When objects fall toward one another, any sideways component of motion matters. A small sideways drift can become an orbit. A slight imbalance in a cloud can become the spin of a star. A rotating disk can become a planetary system. The universe does not need a large original whirl to fill itself with rotating objects. It only needs gravity, motion, and the refusal of angular momentum to disappear without being transferred somewhere else. The most important clue is that rotation appears in different forms. A planet spins around its own axis. A moon orbits a planet orbits a star orbits a galaxy may rotate as a whole, with stars and gas moving in broad paths around its center. These are not identical motions, but they belong to the same family because they involve angular momentum. This term means the amount of turning motion in a system, taking into account both speed and how far mass lies from the axis or center of motion. It is not only a speed, it is a stored relationship between motion and distance. That relationship is why a wide, slowly turning cloud can become a much smaller, faster turning star system. It is also why collapsed stellar remnants can spin with almost unbelievable speed. The beginning of the story is therefore not a dramatic cosmic rotation that sweeps everything along. It is subtler. The universe contains matter in motion, and gravity gathers that matter into regions where tiny sideways differences become important. Once such a difference exists, it can be amplified by collapse. A cloud that barely rotates at first can spin faster as it shrinks. A forming star can inherit motion from the gas that made it. A planet can keep the rotation given to it by impacts and by the disk from which it grew. Much later, even after collisions, tides, magnetic fields, and friction have modified the motion. Some memory of that early angular momentum remains. The calm surface of Earth hides this history well. A day passes so regularly that the turning beneath it feels ordinary. The stars rise and set. The seasons advance. The moon changes phase. These familiar cycles are the visible edges of motion that began long before Earth existed. The planet's rotation is one example within a chain that extends from particles to galaxies, from the formation of stars to the behavior of black holes. The first task is not to ask why Earth alone spins, because Earth is not unusual in that respect. The better starting point is broader and more precise. Across the observable universe, matter almost never falls, forms, or gathers without some sideways motion remaining. That small remainder is enough to change everything. The strongest test of a rotating universe comes from light that has travelled since the early cosmos became transparent. This light is called the cosmic microwave background, and it fills the sky from every direction as a faint record of conditions when the universe was only a few 100,000 years old. It is not perfectly smooth. It contains tiny temperature differences that help reveal where matter was slightly denser or slightly thinner in the young universe. But at the largest scale, the pattern is strikingly even. No clear axis appears in the data that would show the entire observable universe turning like a single object. If the cosmos had a strong overall rotation, that rotation would leave signs. It would stretch the microwave background into a directional pattern. It would make expansion look different along one axis than along another. It would give space a preferred direction, a special line against which other motions could be measured. Modern observations do not show such a global turn. The universe is full of rotating objects, but the universe as a whole does not appear to be rotating in any measurable way. That distinction matters because it removes the simplest possible answer. Everything in space does not spin because the entire cosmos began as one giant spinning system. The evidence points to something more subtle. Local structures rotate while the larger total remains close to balanced. One galaxy can spin one way. Another galaxy can spin another way. And the overall angular momentum can still add up to almost nothing. A planet can rotate around its axis, while its moons and rings carry some of the same motion in different forms. A star-forming cloud can produce a disk, a star, and planets, each with angular momentum distributed among them, without requiring the universe itself to have a single master rotation. This is similar in principle to a crowded system of smaller motions whose directions do not all match. When the motions are added together across enough space, the result can be near zero, even though the individual parts are active. The cosmos can contain turning everywhere without being one rotating object. In cosmology, this is connected to the idea that the universe is broadly homogeneous and isotropic at very large scales. Homogeneous means that, when averaged over enormous distances, matter is spread in a similar way from place to place. Isotropic means that the universe looks broadly similar in every direction. These ideas are not claims that every region is identical. They do not deny the existence of stars, voids, galaxies, clusters, or long filaments of matter. They describe what appears after the largest patterns are averaged. On that scale, there is no obvious center of rotation, and no confirmed cosmic axis around which everything turns. This is important because rotation normally requires an axis. Earth has one, the Sun has one. Though its gas turns at different rates at different latitudes, a galaxy has a disk and a broad rotational plane. A black hole can have spin described by how strongly it drags nearby space-time around itself. For the whole universe, no such confirmed axis has been found. The expansion of space does not behave like the turning of a wheel. It isn't matter flying outward from a central point into empty surroundings. Every distant region moves away from every other distant region as space itself expands. This expansion can happen without any overall spin. The Big Bang is often misunderstood as an explosion from one place, but in modern cosmology, it is better understood as the early hot, dense state of the entire observable universe. Space was not rotating outward from a central hub. Space was expanding everywhere. If there had been a large shared twist in that expansion, it should have affected the structure of the oldest light and the later distribution of galaxies. The absence of a clear signal places strong limits on any possible global rotation. It does not prove that every imaginable form of rotation is impossible in regions beyond observation, but it shows that within the observable universe, any overall spin must be extremely small. This makes the abundance of local spin more interesting, not less. It means rotation did not need a cosmic starting whirl. It could arise naturally inside a universe whose total angular momentum remains balanced. The difference between total and local motion is familiar in physics. A system can have no net momentum while still containing motion inside it. Gas in a sealed container may have no overall drift through a room, yet its molecules move rapidly in all directions. The average motion cancels, but the internal motion remains real. Angular momentum can behave in a related way. If enough regions rotate in different directions, the sum can be close to zero. While each region still has its own history of turning, this helps explain why there is no contradiction between a non-rotating universe and rotating galaxies. The large-scale balance does not erase the local motions. It only says that those motions are not organized into one universal spin. A galaxy does not need the whole cosmos to rotate in order to rotate itself. It needs matter with a slight sideways motion as gravity gathers it. A star does not need a spinning universe in order to spin. It needs a collapsing cloud that does not fall inward with perfect symmetry. A planet does not need a cosmic axis to turn beneath its sky. It needs formation inside a rotating disk, along with impacts, tides, and exchanges of angular momentum that shape its final motion. The early universe supplied the necessary ingredients without assigning one common direction to all of them. It contained matter, radiation, gravity, and small differences in density. It also contained motion. These motions were not arranged in a perfectly smooth way. They varied from place to place, and that variation mattered. Perfect symmetry would be a very special condition. If every particle in a collapsing region moved in a way that exactly cancelled every other sideways motion, the region might fall inward without forming a rotating structure. But the real universe was not arranged with that exact cancellation in every future star-forming cloud. Tiny departures from perfect balance were enough to leave a remainder. That remainder became angular momentum. At first it could be almost unnoticeable. A vast cloud of gas could turn so slowly that the motion would seem unimportant compared with its size. Yet gravity changes the meaning of small rotation. When a cloud contracts, the same angular momentum must be carried by material that is now closer to the center. Unless that angular momentum is transferred away, the rotation rate increases. A barely turning cloud becomes a more clearly rotating cloud. As collapse continues, the structure flattens, the central region grows dense, and the remaining gas organizes into a disk. The star and planets that emerge from that disk inherit a history that began as a small imbalance, not as a command from the whole universe. This is why the question of cosmic spin has to be separated into levels. At the largest observable level, there is no measured overall rotation. At the level of galaxies, stars, planets, moons, and smaller systems, rotation appears because gravity amplifies small angular motions that were already present locally. The same law can preserve balance across the whole. while intensifying motion inside the parts. No special contradiction is required. The universe can begin with no net spin and still make countless spinning structures because local angular momentum can appear in positive and negative directions, in tilted planes, in opposite rotations, and in complicated exchanges between objects. Collisions can move angular momentum from one body to another. Tides can slow a moon's rotation and transfer motion into an orbit. Magnetic fields can carry angular momentum away from young stars. Accretion disks can feed black holes while spreading some material outward. These processes do not create a universal spin. They redistribute angular momentum inside smaller systems. The result is a cosmos where rotation is common, but alignment is not absolute. Many disks have their own orientations. Many stars are tilted relative to their planets. Many galaxies rotate in directions unrelated to the view from Earth. This lack of universal agreement is part of the evidence. If all spin came from one original cosmic rotation, a stronger shared pattern might be expected. Instead, the universe shows a mixture of directions shaped by local formation histories. That mixture points toward a calmer and more precise explanation. Rotation is not imposed everywhere from above. It emerges wherever matter collapses with even a slight sideways remainder. The oldest light shows no clear master turn. The largest surveys reveal no confirmed cosmic wheel. Yet within that near-balanced whole, gravity keeps finding the tiny imperfections that matter. The next step is to look at those imperfections more closely, because the origin of spin is not hidden in a grand rotation of everything, but in the small uneven motions of early gas that fail to cancel perfectly. The first structures did not begin as finished objects. They began as small differences in a nearly uniform field of matter and radiation, preserved in the early universe like faint variations in temperature and density. After the hot young cosmos cooled enough for atoms to form, light could travel freely, and the matter left behind was mostly hydrogen, with helium and trace amounts of other light elements. This gas did not spread with perfect smoothness. Some regions were slightly denser than their surroundings, not by much, but enough for gravity to act differently there. A denser region pulled a little more strongly on nearby matter. That extra pull made the region denser still. Over long spans of time, a small excess became a growing concentration. This is the beginning of the path from featureless gas to galaxies, stars, and planets. But density alone does not fully explain spin. A cloud can be heavier than its surroundings and still, in a simplified picture, collapse straight inward. The reason real clouds do not usually behave with that perfect symmetry is that the matter inside them already has motion. Particles move, gas streams, dark matter, which does not shine but adds gravity, gathers into broad halos that guide ordinary matter into deeper wells. Neighbouring regions tug on one another. None of this motion is arranged with exact balance. In a collapsing patch, some material approaches from one side, some from another, and the directions are never perfectly paired. When all those motions are added together, most may cancel, but most is not all. What remains can be very small, yet it has a direction around the centre of mass. That remainder is angular momentum. It is the seed of rotation. The important point is that this seed does not need to be large. A future star-forming cloud may begin with only a slow, uneven drift, spread across a region so large that its turning would be almost impossible to notice. At that stage, gravity is doing the more obvious work. It gathers matter into filaments, clumps, and halos. Gas falls inward along paths shaped by the surrounding mass. Pressure resists collapse, heating develops, and radiation begins to matter. Within this larger process, the slight sideways component might seem secondary, yet it cannot be ignored. because inward collapse changes the scale of the system, while angular momentum tends to remain conserved unless it is transferred away. The cloud may shrink by an enormous factor. Material that once lay far from the centre now lies closer. The same angular momentum, held by a smaller distribution of mass, requires faster rotation. In this way, a tiny imbalance becomes visible not because it was strong at the beginning, but because collapse concentrates it. The early universe therefore did not need to assign every cloud a deliberate spin. It only needed to avoid perfect cancellation. Perfect cancellation is difficult to arrange in a real gravitational environment. A cloud is not isolated from the rest of the cosmos. It is pulled by nearby clumps. It is stretched by tidal forces, which are differences in gravity from one side of a region to another. These tidal forces can twist a forming structure slightly as it grows. The effect is subtle, but over time it helps give dark matter halos and gas clouds their angular momentum. This process is often described in cosmology as tidal torque, meaning that surrounding matter can apply a turning influence to a region before it fully collapses. It is not a separate force added to gravity. It is gravity acting unevenly across space. One side of a cloud may be pulled a little differently than the other, because the shape of the cloud is not perfectly round and the surrounding mass is not perfectly arranged. The result can include a slight twist. Once collapse continues, that twist is amplified. This helps explain why rotation appears so naturally without requiring a rotating universe. Local structure grows inside an uneven gravitational field, and uneven gravity does not only pull inward, it can also change orientation and produce a small amount of turning motion. Even when the initial angular momentum is modest, its later consequences are large. A collapsing cloud cannot simply place all its gas into the central object, because the rotating material has too much angular momentum to fall straight in. The material tends to settle into a disk. Some gas moves inward, feeding the central region. Some moves outward, carrying away angular momentum so that the inner gas can fall closer. The formation of a star is therefore not only a story of gravity overcoming pressure, it is also a story of angular momentum being redistributed. Without redistribution, too much rotation would prevent material from reaching the center. Magnetic fields, turbulence, jets, winds, and interactions within the disk can all help move angular momentum from one part of the system to another. The final star contains only part of the original cloud's angular momentum. The rest may be carried by the disk, by forming planets, by outflows, or by material that never becomes part of the star at all. This distribution matters because it shows that spin is not a simple inheritance passed unchanged from cloud to star to planet. It is a budget that has to be moved around. Some objects gain, others lose. A young star may be slowed by magnetic connections to its disk. Planets may take up a large share of the angular momentum in their orbits. Moons can exchange angular momentum with their planets through tides. Collisions can tilt or reverse rotations. But the first entry in the budget comes from those early imperfect motions. Once angular momentum exists, later events reshape it rather than erase its importance. The system may become more complex, but it does not return to a state of clean stillness. The same principle applies beyond individual stars. Galaxies grow from matter falling into large dark matter halos. Gas enters these halos along filaments of the cosmic web, cools, and settles where it can. The gas does not arrive from all directions equally. It carries angular momentum determined by the history of the halo, the pull of neighbouring structures, and the paths along which matter has fallen. As the gas cools, it can form a rotating disk. Stars born from that gas inherit the motion of the system in their orbits around the galactic centre. A galaxy is therefore not a cloud that decided to spin after becoming a galaxy. Its rotation is tied to the way matter gathered in the first place. The large disk seen in many spiral galaxies is the visible result of angular momentum surviving collapse on a vast scale. This does not mean every galaxy becomes a clean, orderly disk. Some galaxies are elliptical, with stars moving along more varied paths. Mergers can disturb disks, randomize orbits, or build larger systems with less obvious rotation. Even there, angular momentum is not absent. It may be spread among stellar motions, halo motion, streams, and the orbital paths of merging galaxies. The form changes, the underlying accounting remains. Rotation is common because the universe builds structure through uneven collapse, and uneven collapse almost always leaves some sideways motion behind. The phrase tiny imbalance can sound too small for the consequences it produces, but this is one of the quiet strengths of gravity. Gravity acts over distance and over time. It does not require large initial differences to create large later structures. A region only slightly denser than average can become the site of a galaxy. A cloud with only a faint net rotation can produce a disk. A star-forming core with a small angular momentum can generate a system where planets orbit in a shared direction. The early conditions are modest. The later results are organized and durable. What matters is not that the first motion was dramatic. What matters is that it was not exactly zero. This also explains why cosmic spin has so many local directions. If angular momentum grows from local imbalances and local gravitational torques, then different regions should not all align. One cloud may rotate one way, another cloud may rotate at a tilted angle, and a third may be shaped by later collision or merger. The universe does not impose a single orientation. It supplies many local histories. Each history carries its own small remainder of motion, and gravity enlarges the consequence. In this sense, the origin of spin is not mysterious because it violates stillness. It is mysterious only because everyday experience makes stillness seem natural. On cosmic scales, stillness is the special case. Motion is the ordinary starting condition, and perfect cancellation is the rare demand. The young universe did not have to be a whirlpool. It only had to be slightly uneven, filled with matter that moved, fell, tugged, and failed to cancel every sideways component. From that failure came the angular momentum of clouds, disks, stars, planets, and galaxies. The next part of the story is the law that allows such small beginnings to survive collapse and grow more obvious as matter draws inward. Angular momentum is the quiet rule that carries the small beginnings of rotation into the finished structures of space. It is not a separate substance inside matter, and it is not a force pushing objects around. It is a conserved property of motion. When mass moves around a center or turns around an axis, that motion has angular momentum. The amount depends on how fast the mass is moving and how far that mass lies from the center of rotation. A broad, slowly turning system can carry a great deal of angular momentum because its material is spread over a wide distance. A compact system can carry the same amount only by turning faster, unless some of that angular momentum is transferred away. This is the key to why cosmic rotation becomes stronger during collapse. Gravity pulls matter inward, distances shrink, but the angular momentum of the system cannot simply vanish. If no outside influence removes it, the motion adjusts, the rotation rate increases. What began as a slow drift across a large region becomes a more obvious spin as the same material draws closer together. This rule is called conservation because the total amount is preserved within a closed system. Real cosmic systems are not perfectly closed because they exchange matter, radiation, magnetic stresses, and gravitational pulls with their surroundings. Even so, conservation remains the central guide. Angular momentum may move from one region to another, from a star to a disk, from a planet to a moon's orbit, or from inner gas to outer gas. But it does not disappear without being carried somewhere. This makes it one of the most important accounting rules in astronomy. Energy can change form. Matter can heat, cool, fuse, break apart, or fall inward. Angular momentum must still be tracked, because it controls whether material reaches a center, remains in orbit, spreads into a disk, or escapes into space in a collapsing cloud. This becomes unavoidable. Gas that falls almost directly inward can feed the forming center. Gas with more sideways motion cannot fall straight in. It circles. As more material joins the same region, collisions and pressure help the gas share its motion. The cloud flattens, and a disk begins to form. This disk is not created because the cloud wants a flat shape. It forms because angular momentum prevents all the gas from taking the shortest inward path. The inward pull of gravity and the sideways motion of the gas settle into a structure where material can keep moving around the center, while slowly finding ways to lose enough angular momentum to fall farther inward. The disk is therefore a working solution to a physical problem. Gravity wants concentration. Angular momentum resists direct collapse. The result is organized rotation inside the disk. Angular momentum continues to move. Gas closer to the forming star must lose some of it in order to fall inward. Gas farther out may gain some and move outward. Magnetic fields can connect rotating gas to surrounding material and help carry angular momentum away. Jets and winds from young stars can also remove rotating material from the system. These details matter because they prevent a common misunderstanding. Conservation of angular momentum does not mean every part of a forming star system keeps exactly the same rotation it began with. It means the total must be balanced. A central star can become relatively slow compared with the original cloud because much of the angular momentum remains in the disk or is carried away. Planets can hold a large share of the system's angular momentum in their orbits, even though they contain only a smaller share of the total mass. This is why the distribution of angular momentum in a solar system is not the same as the distribution of matter. A star may hold most of the mass, while planets and surrounding material carry much of the turning motion. The same conservation law also explains why shrinking objects can become extreme rotators. A star begins as a huge object, with gas moving at different depths and latitudes. During most of its life, pressure from hot gas and radiation balances gravity, so the star keeps a stable size. When a massive star exhausts the fuel that supports its core, that balance fails in the center. The core collapses. Material that was once spread across a region thousands of miles wide can be compressed into a remnant only miles across. If angular momentum is not fully removed, the rotation must accelerate sharply. This is one reason neutron stars can spin so rapidly. Their speed is not created from nowhere. It is inherited from the earlier star and intensified by collapse. The smaller the final object becomes, the greater the effect, as long as the angular momentum remains. This is the same principle that operates in young star-forming clouds, but carried to a far more compressed state. Gravity reduces the size. Conservation protects the turning budget. The remnant responds by spinning faster. Black holes bring the rule into an even more severe form. When matter collapses past the point where light can escape, angular momentum still remains part of the black hole's description. A rotating black hole is not only a mass with an event horizon, it also has spin, and that spin affects the space-time around it. Near such an object, rotation is no longer only the motion of matter through space. The geometry of space and time itself is dragged in the direction of the black hole's spin. This effect is called frame dragging. It has no ordinary comparison that captures it fully, but the idea can be stated simply. Close to a rotating black hole, space-time is not a passive background. The rotation of the black hole influences the paths that matter, and light can follow. Angular momentum, compressed into one of the most extreme objects allowed by known physics, becomes part of the surrounding environment. Before reaching those extremes, the same law shapes more familiar systems. Earth's rotation is slowly changing because angular momentum is exchanged with the Moon. Tides raised by the Moon create bulges in Earth's oceans and solid body. Because Earth rotates faster than the Moon orbits, those tidal bulges are carried slightly ahead of the line between Earth and the Moon. Their gravity pulls on the Moon and gradually gives the Moon more orbital angular momentum. The Moon moves slowly farther away, while Earth's rotation slows by a very small amount over long times. Nothing mystical is happening. Angular momentum is being transferred from Earth's spin into the Moon's orbit. The total accounting remains the key. A similar process has already locked the Moon's rotation to its orbit, so the Moon keeps nearly the same face turned toward Earth. Tidal interactions can slow rotation, synchronize motion, and reshape the future of planets and moons without breaking conservation. In young systems, impacts add another layer. A forming planet grows through collisions with smaller bodies. Each incoming body carries motion. Some strikes add to the planet's rotation, others subtract from it or tilt its axis. A large impact can leave a planet rotating at an unusual angle, or even in a direction opposite to most neighbouring planets. This is why the shared rotation of a protoplanetary disk gives a general pattern, but not a perfect one. Conservation still applies during collisions, but the angular momentum is redistributed among spin, orbit, heat, ejected material, and fragments. The final state records a history of exchanges. A planet's day is not only a memory of the disk from which it formed, it is also a memory of impacts, tides, internal changes, and later gravitational interactions. This is why rotation in space is both orderly and varied. The law is steady, but the histories are different. At galactic scales, conservation of angular momentum helps explain why matter does not simply fall into the centre of a forming galaxy. Gas entering a dark matter halo carries angular momentum from earlier tidal torques and infall. As the gas cools, it can settle into a broad, rotating disk. Stars then form inside that disk and continue orbiting the galactic centre. Gravity keeps pulling inward, but angular momentum gives the matter a way to remain extended. A galaxy disk is not a frozen object. Gas clouds collide. Stars form. Supernovae stir the surrounding medium. Dark matter shapes the gravitational field. Other galaxies pass nearby or merge. Through all of this, angular momentum is exchanged and rearranged. Some can be moved into outer halos or tidal streams. Some can be carried by gas flowing inward toward a central black hole. Some remains in the rotating disk. The visible shape of a galaxy is therefore a record of how gravity and angular momentum have negotiated over cosmic time. This negotiation is the reason spin becomes so common. Gravity alone pulls matter together. Motion gives that collapse direction and structure. Conservation keeps the sideways part from being erased casually. A very small initial angular momentum can become decisive after contraction, because the system's size changes while the turning budget must be preserved or transferred. This is why slow early motions can lead to fast later rotation, why disks form around young stars and black holes, why planets inherit shared orbital directions, and why collapsed remnants can spin at rates that seem disconnected from their original stars until the change in size is considered. The law does not make every object spin forever at the same rate. Friction, tides, magnetic fields, radiation, and collisions can all change individual motions. But every change has to send angular momentum somewhere. That requirement gives rotation its persistence. The universe does not need perfect stillness to be disturbed by spin. It begins with motion already present, and once gravity concentrates matter, conservation makes even modest rotation difficult to ignore. The next consequence appears when collapsing gas can no longer remain round. Because angular momentum does not only make objects turn faster, it also changes the shapes in which stars and planets are able to form. A collapsing cloud begins as something irregular, not as a clean sphere falling evenly toward one point. It contains gas at different densities, dust mixed through colder regions, magnetic fields threading through the material, and motions left over from the larger environment that produced it. Gravity pulls all of this inward, but the inward motion is never perfectly radial. There is always some sideways drift, some uneven flow, some small rotation inherited from the cloud's earlier life. As the cloud shrinks, conservation of angular momentum strengthens that rotation, and the shape of the collapse begins to change. The gas can no longer fall from every direction straight into the center. Material moving sideways around the center meets other material, collides, shares momentum, heats, cools, and gradually settles into the plane where its angular motion can be carried most efficiently. The result is a disk. This disk is an important shape in astronomy because it appears whenever gravity is strong enough to gather matter, but angular momentum is strong enough to prevent direct infall. Around young stars, compact stellar remnants, and black holes, the same basic problem returns. Matter is pulled inward, but it arrives with too much angular momentum to drop straight down. The disk forms while the system moves some angular momentum outward and some material inward, in a star-forming region. This process begins inside a cold molecular cloud. These clouds are made mostly of hydrogen molecules, with helium and small amounts of dust and heavier elements. They can stretch across many light years and contain enough mass to form many stars. Within them, denser pockets become unstable and start to contract. At first, the collapse may look like a movement toward greater concentration, but as the pocket grows smaller, rotation becomes more important. Gas falling along the axis of rotation can move relatively easily toward the center. Gas near the equatorial region carries more sideways motion and resists direct collapse. Over time, the structure flattens. A dense central object forms, while a rotating disk surrounds it. The central object is called a protostar, because it has not yet settled into the long stable phase of a true star. It is still gathering mass. It is still buried in gas and dust. Its light may be hidden at visible wavelengths. While infrared observations reveal the warmth of material falling inward and the outline of the disk around it. The disk is not a quiet ring of leftover debris. It is active, turbulent, and essential to the growth of the star. Gas in the disk orbits the protostar, but it also slowly spirals inward as angular momentum is transported away from the inner regions. Turbulence, magnetic fields, gravitational instabilities, and interactions between different layers of gas can all contribute. The basic requirement is simple. Inner gas cannot reach the protostar unless it gives up some angular momentum. Outer gas or outflowing material must receive it. This exchange allows accretion to continue. Accretion means the gradual addition of material to a growing object. In a young stellar system, accretion is how the protostar gains much of its final mass. The process is often accompanied by jets, narrow streams of material launched along the rotation axis. These jets may look, at first, like matter escaping in contradiction to collapse. In fact, they are part of the same system. They can carry away energy and angular momentum, helping the remaining material move inward. The presence of a disk and jets around a young star is therefore not incidental. It is evidence that the system is solving the angular momentum problem created by its own formation. The disk also becomes the setting for planets. Dust grains inside it collide and stick. At first through simple contact and surface forces, later through gravity as larger bodies form. Small particles become pebbles. Pebbles gather into planetesimals, which are building blocks large enough for their own gravity to matter. Over time, collisions and mergers produce planetary embryos, and some embryos become planets. The whole process occurs inside a rotating disk, so the forming planets naturally inherit orbital motion around the star in the same broad direction. This is why a planetary system often has a shared plane and a shared sense of circulation. The pattern is not perfect, because collisions, migrations, and gravitational encounters alter the final arrangement, but the disk provides the starting order. The planets are not placed around the star one by one. They grow from a rotating environment that already contains a preferred plane. The flatness of such systems is a direct consequence of repeated collisions and shared angular momentum. When particles orbit at different angles, their paths cross more often. Collisions damp the vertical motions, converting some energy into heat while preserving the overall angular momentum. The remaining material settles closer to a common plane. In this way, a cloud that began as a three-dimensional structure can produce a flattened disk, and the disk can produce planets whose orbits lie near the same surface. The early disk can be violent on small scales, with shocks, impacts, turbulence, and local instabilities. But the long-term outcome is still organized because angular momentum gives the system a preferred direction, and because collisions remove motions that do not fit that shared pattern. The same reasoning helps explain why disks are seen in other environments. Around a white dwarf, gas stripped from a companion star can form an accretion disk. Around a neutron star, infalling material can spiral inward under extreme gravity, heating until it emits powerful radiation. Around a black hole, gas can form a disk so hot that it shines brightly before crossing the event horizon. In each case, matter rarely arrives with exactly zero angular momentum. It cannot fall straight in. It must orbit, lose angular momentum, and move inward step by step. The details differ with temperature, density, magnetic field, and gravity. But the shape recurs because the underlying physics recurs. Disks are common answers to the question of how matter approaches a center without being able to fall directly into it. In a young planetary system, the disk also explains why the central star does not simply absorb everything nearby. Some material falls inward, but some remains in orbit long enough to build planets, moons, asteroids, and comets. The star gains most of the mass, while the disk preserves much of the angular momentum. This division is one of the reasons the solar system has its present architecture. The Sun contains almost all the mass, but the planets, especially the large outer planets, carry most of the orbital angular momentum. That fact would be difficult to understand if formation were imagined as simple inward collapse. It makes sense when the system is treated as a rotating cloud whose angular momentum had to be distributed. The disk allowed the center to grow while leaving a broad reservoir of orbiting material behind. Some material in that reservoir was ejected, some fell into the young sun, some remained as smaller bodies. Some became part of moons and rings, but all of it belonged to the same angular momentum economy. This is why the direction of planetary motion carries information about origin. In the solar system, most planets orbit the Sun in the same direction that the Sun rotates, and most rotate on their axes in that general sense as well. This common direction reflects the rotating disk from which they formed. It does not mean that every later detail stayed unchanged. Venus rotates slowly in the opposite direction from most planets. Uranus is tilted so far that it rolls around the Sun with its axis lying nearly in its orbital plane. These exceptions point to later history impacts, tides, internal evolution, or gravitational interactions that modified the original spin. Exceptions do not erase the disk pattern. They reveal that the pattern was later disturbed. The disk gives the rule, and the unusual cases show where history complicated it. The most useful way to understand a protoplanetary disk is to see it as both a birthplace and a record. It is a birthplace because it supplies the material from which planets grow. It is a record because its flatness, rotation, gaps, rings, and flows reveal how angular momentum is being moved through the system. Modern telescopes have observed young disks with dark lanes and ring-like structures that may be connected to forming planets, changes in dust grain size, or pressure patterns in the gas. These observations show that planet formation is an active process visible around young stars. The disks differ from one system to another, but the central logic remains stable. Collapse concentrates matter. Angular momentum prevents direct collapse. A disk forms. Within that disk, the material sorts itself into inward flow, outward transport, and long-lived orbiting structures. From those structures, planets can emerge. The strange reason everything in space spins is therefore not only that objects began with motion, it is that gravity makes motion matter more as systems contract. A faint rotation in a cloud becomes a disk because there is no easier way for the cloud to conserve angular momentum while forming a center. The disk then passes that motion into the orbits and rotations of the bodies that grow inside it. Stars and planets are not born in spite of spin. They are born through the management of spin. The next step is to look at the worlds formed inside such disks. Because their shared motion reveals the original order, while their unusual tilts and backward rotations show how later events can rewrite part of that order, planets preserve the memory of the disk they formed from, but they do not preserve it perfectly. In a young system, gas and dust circle the central star in a shared direction, because they belong to the same rotating structure. Bodies that grow inside that disk inherit this motion first as orbits. A small grain does not choose a path around the star. It is carried by the gas, affected by drag, and drawn into the same broad flow as the rest of the disk. As grains become pebbles, and pebbles become larger bodies, their individual motions remain tied to that circulation. Collisions remove many of the more tilted or crossing paths, while the overall angular momentum of the disk keeps a preferred direction. By the time planets begin to emerge, the system already has a strong pattern. Most planets will orbit the star in nearly the same plane, and most will move around it in the same direction. This is why the solar system looks ordered at first glance. The major planets do not orbit the Sun from random angles. Their paths lie close to a common plane called the ecliptic, which reflects the flattened disk from which they grew. Their motion around the Sun is also shared. Seen from above the Sun's north pole, the planets orbit counterclockwise. This common orbital direction is one of the clearest remaining signs that the solar system formed from a rotating disk, rather than from unrelated objects captured one at a time. If the planets had arrived separately from random directions, their orbits would likely be far more scattered in angle and direction. Instead, the broad order is still visible after billions of years. The disk has vanished, but the angular momentum it carried remains written into planetary motion. Rotation on a planet's own axis is related to this same history, though it is more easily modified. A planet forms through many impacts, not through smooth accumulation alone. Each incoming body delivers mass, energy, and angular momentum. If a growing planet is struck in a way that supports its existing spin, it rotates faster. If it is struck from another direction, its spin can slow, tilt, or change orientation. The planet's final day length and axial tilt are therefore not determined only by the original disk. They are also shaped by the last major stages of growth, when large bodies collide and exchange angular momentum. This helps explain why the orbital pattern of the planets is more consistent than their individual rotations. Orbits reflect the large-scale disk more strongly. Axial spins remember a more detailed and sometimes more violent local history. Earth carries both kinds of information. Its orbit follows the shared direction of the solar system. Its rotation is also broadly aligned with that direction, giving the planet a regular day and night cycle. But Earth's axis is tilted, and that tilt is central to the seasons. The leading explanation for the formation of the Moon involves a giant impact early in Earth's history. When a Mars-sized body struck the growing planet and sent debris into orbit. That event would have changed Earth's spin and created a disk of material from which the Moon later formed. The present Earth-Moon system is therefore not only a quiet inheritance from the solar nebula, it is also the result of a major collision and the long tidal evolution that followed. Over time, the Moon has pulled on Earth's oceans and solid body, slowly lengthening Earth's day while moving gradually farther away. The rotation of Earth is still changing, not quickly in ordinary experience, but measurably across geological time. Mars offers a different example. It rotates in a direction similar to Earth, and has a day length not far from Earth's, but its small moons, Phobos and Deimos, occupy close and unusual orbits. Their origin remains debated, with possibilities including captured asteroids or debris from impacts around Mars. Whatever their precise history, they show how planetary systems preserve more than one layer of angular momentum. The planet has its spin, the moons have their orbits, tides continue to alter the arrangement, Phobos is slowly spiraling inward and will eventually either break apart or strike Mars, while Deimos is moving more slowly outward. These changes are not exceptions to conservation. They are examples of angular momentum being exchanged among bodies over time. Jupiter shows the power of rapid rotation on a much larger world. It spins faster than any other planet in the solar system, completing a day in less than 10 Earth hours, because it is made mostly of fluid material rather than solid rock. This rotation helps flatten the planet noticeably, widening it at the equator and narrowing it at the poles. The rapid spin also contributes to strong atmospheric bands and interacts with the planet's magnetic field. Jupiter's many moons orbit within a system that also carries angular momentum, and several of the large moons move in the same general direction as the planet's rotation. Yet Jupiter also has many smaller outer moons with irregular, tilted, or backward orbits, likely captured or altered by later interactions. The broad pattern of formation remains. While the outer details record a more complicated history, Saturn follows a similar principle. Its rings orbit in the planet's equatorial plane, making them a clear example of flattened material governed by gravity and angular momentum. Ring particles do not hover in place. They orbit Saturn, colliding gently and remaining confined to a thin structure because motions that rise far above or below the ring plane tend to be damped by repeated encounters. The rings may come from disrupted moons, leftover material, or a combination of sources, but their flatness reflects the same physical rule seen in young disks. Matter with angular momentum around a central body naturally organizes into a plane when collisions and gravity have time to work. The rings are not a separate mystery from cosmic spin. They're a smaller, cleaner expression of it. Venus and Uranus show why the solar system's order cannot be described as perfect. Venus rotates in the opposite direction from most planets, and it does so very slowly. A solar day on Venus is extremely long, longer than its year in a particular technical sense, because its backward rotation and orbit combine in an unusual way. The reason for this retrograde rotation is still studied. Possible explanations include large impacts in the early solar system, strong tidal effects from the Sun, and interactions between Venus's thick atmosphere and its rotation. The exact path may involve more than one process. What matters for the larger story is that Venus did not need to form outside the rotating disk to become unusual. A planet can begin within the shared order and later have its spin altered. Uranus is stranger in a different way. Its axis is tilted by about 98 degrees, so the planet rotates almost on its side relative to its orbit. This extreme tilt may have been produced by one or more giant impacts during formation, or by gravitational interactions that shifted its spin axis early in its history. Its major moons orbit close to the plane of its equator, which means the whole satellite system appears tilted along with the planet. That detail suggests the unusual orientation became part of the local system, not merely a surface feature of the planet alone. Uranus therefore records an early disturbance large enough to redirect the angular momentum of a growing world and its surrounding material. The case is a reminder that shared formation does not prevent later change. It only defines the starting conditions that later events must modify. Even smaller bodies show this mixture of inheritance and alteration. Asteroids rotate because they formed through collisions and carried angular momentum from the early solar system. Some spin slowly, others rotate so quickly that loose material can shift or escape from their surfaces. Sunlight can also change asteroid rotation over long periods through a subtle effect involving absorbed and re-emitted heat. Comets rotate as well, and jets of gas from their warming surfaces can change their spin. These objects are not large enough to keep stable atmospheres or complex internal systems like planets, but they still obey the same accounting. Their shapes, tumbling motions, and changing rotations preserve the influence of impacts, sunlight, outgassing, and gravity. The solar system's shared rotation is therefore best understood as a layered record. The first layer comes from the protoplanetary disk, which gives the planets their common orbital plane and direction. The second layer comes from planet growth, where impacts determine much of each world's axial spin and tilt. The third layer comes from long-term evolution, including tides, atmospheric effects, resonances, and smaller collisions. These layers do not conflict. They explain why there is order without uniformity. Most planets follow the disk's direction around the Sun, but their days, tilts, moons, and smaller companions reveal additional histories. The result is neither random nor perfectly arranged. It is a system governed by conservation, shaped by formation, and edited by time. The strange reason planets spin is not a single event, but a continuing transfer of angular momentum from disk to world, from impact to axis, from planet to moon, and from one orbit to another. The next scale is smaller in size but deeper in meaning, because angular momentum is not limited to planets and stars. It also appears inside matter itself, where the word spin begins to mean something more precise and less familiar. At the scale of atoms, rotation becomes harder to picture and more important to define carefully. An electron does not spin like a planet, and a proton is not a small solid ball turning on an invisible axle. The word spin remains because particles carry a form of angular momentum that behaves in some ways like rotation, especially in how it interacts with magnetic fields. But quantum spin is intrinsic. It is built into the particle as one of its basic properties, like electric charge or mass. Nothing inside the electron has to be imagined as rotating through ordinary space. In fact, treating it as a tiny sphere spinning in the everyday sense leads to impossible results. The surface would have to move faster than light, and the model would still fail to explain the measured behavior, so the meaning has to shift. Spin at this level is not a visible turning motion. It is a precise quantum property that tells matter how to respond, combine, and organize. This can feel like a departure from the rotation of planets and stars, yet it belongs to the same broader family because it is still angular momentum. The difference is that the angular momentum is no longer produced by a large object moving around a center. It is part of the identity of the particle itself. Every electron carries spin. Protons and neutrons carry spin as well, though they are made of smaller particles called quarks, whose own spins and motions combine in complicated ways. Photons, the particles of light, also carry angular momentum. In the quantum world, angular momentum is not allowed to take just any value. It comes in fixed units, according to the rules of quantum mechanics. That discreteness is one of the reasons atoms have structure instead of collapsing into a featureless blur. The connection between spin and matter becomes clear in the behavior of electrons around atomic nuclei. Electrons occupy quantum states, which are allowed arrangements described by energy, shape, and angular momentum. One of the most important rules is the Pauli exclusion principle. It says that two electrons of the same kind cannot occupy exactly the same quantum state at the same time. Spin is part of what defines that state, because electrons can have different spin orientations within an orbital. Atoms can build shells and chemical patterns instead of placing all electrons into the lowest available condition. This rule helps give the periodic table its structure. It helps explain why carbon bonds as it does, why oxygen behaves differently from neon, and why matter has the variety needed for rocks, oceans, atmospheres, and living chemistry. The spin of an electron is therefore not an isolated curiosity. It is part of the quiet machinery that makes ordinary matter stable and diverse. Magnetic fields reveal another side of spin. A charged particle with angular momentum can act as a tiny magnetic system. Electrons have magnetic moments, meaning they respond to magnetic fields and help create magnetism in materials. In many substances, the magnetic effects of electrons cancel because spins are paired in opposite orientations. In some materials, especially certain forms of iron, cobalt, and nickel, many electron spins can align in the same general direction. When that happens, the material becomes magnetic on a scale large enough to affect compasses, motors, generators, and planetary interiors. A magnet is not simply a piece of matter with a mysterious pull. It is an organized state in which countless quantum spins contribute to a larger field. The familiar north and south behavior of a magnet begins in the angular momentum of particles too small to see. This is one of the clearest bridges between quantum spin and large-scale physical effects. What appears as a steady magnetic force in daily experience is connected to the rules that govern electrons inside atoms. The same principle reaches into astronomy. Stars and planets often have magnetic fields because charged material moves inside them, but the behavior of that material depends on atomic and particle properties. In Earth, the magnetic field is generated mainly by motion in the liquid outer core, where electrically conducting iron alloy circulates as the planet cools and rotates. Rotation helps organize that motion, and the resulting dynamo produces a magnetic field that surrounds the planet. Yet the conductivity of the material, the way electrons move through it, and the magnetic response of matter all depend on quantum rules. The planetary field is not produced by electron spin alone, but electron behavior is part of the physical foundation that allows electric currents and magnetic fields to exist. At the scale of the Sun, hot plasma carries electric charge through a moving, rotating body. The solar magnetic field twists, reverses, and reconnects, shaping sunspots, flares, and streams of charged particle. Again, the visible behavior belongs to a large fluid system, but the possibility of electromagnetic fields is rooted in the properties of charged particles. Quantum spin does not replace planetary and stellar rotation. It connects the smallest descriptions of matter to the larger phenomena that rotation helps organize. The distinction between orbital angular momentum and spin also matters inside atoms. An electron in an atom can have angular momentum associated with its quantum state around the nucleus. Though it is not orbiting like a small moon, it can also have intrinsic spin. These forms can interact. This interaction helps split energy levels in subtle ways, leaving signatures in the light atoms absorb or emit. Astronomers depend on such signatures. When light from a star, nebula, or distant galaxy is spread into a spectrum, dark and bright lines reveal which atoms are present, how hot the gas is, how dense it may be, and how it moves. Some of those details depend on angular momentum at the quantum level. The chemistry of distant worlds, the composition of stars, and the motion of galaxies can be studied because atoms follow reliable rules when their electrons change states. In this indirect way, the spin hidden inside matter helps make the universe readable. A telescope does not touch a star. It receives light. That light carries information shaped by quantum transitions, magnetic fields, and angular momentum. The smallest rules become tools for understanding the largest objects. There is also a deeper reason spin cannot be treated as a minor feature. Particles are divided into broad families according to their spin. Matter particles such as electrons and quarks have half-integer spin, while force-carrying particles such as photons have integer spin. This difference controls how they behave in groups. Matter particles resist being stacked into identical states, while some force carriers can gather into the same state more freely. The stability of atoms, the pressure inside white dwarfs and neutron stars, and the behavior of light all depend on these quantum distinctions. In a white dwarf, electrons are squeezed so tightly that the Pauli exclusion principle creates a pressure resisting further collapse. In a neutron star, a related resistance involving neutrons helps support matter under conditions far beyond ordinary density. Though gravity is so strong that other nuclear forces and relativity also become essential. These compact objects connect the smallest rules of spin to the fate of dead stars. A quantum property that cannot be pictured as ordinary rotation becomes part of the reason a star's remnant can avoid immediate collapse, at least up to a limit. That connection shows how deeply angular momentum enters the structure of the universe. It appears as the spin of particles, the organization of atoms, the magnetic behavior of materials, the pressure of compact matter, and the rotation of large bodies. These are not all the same motion, and they should not be blurred together as if an electron were merely a tiny planet. The better understanding is more careful. Angular momentum is a basic language used by nature at many scales. Sometimes it appears as an orbit. Sometimes it appears as the turning of a planet. Sometimes it appears as the circulation of a galactic disk. Sometimes it appears as intrinsic spin, with no ordinary surface moving through space. The name is shared because the underlying conservation laws and symmetries are related, even when the physical picture changes. This is why the question of why everything spins must eventually pass through quantum matter. The universe is not only filled with rotating worlds and orbiting stars, it is built from particles whose allowed states already include angular momentum, atoms, magnetic fields, light, and compact stellar remnants all carry the influence of that fact. Large cosmic structures show rotation in a visible way, but the habit of angular momentum begins much deeper than any disk or planet. The next scale returns to stars, where ordinary rotation and magnetic fields meet inside glowing plasma, and where a star's spin can shape its surface, its activity, and the environment around its planets. A star is not a solid sphere turning as one piece. It is a body of plasma, a hot gas of charged particles, held together by gravity and supported by pressure from heat and radiation. Because it is fluid, different parts can rotate at different rates. The Sun shows this clearly. Near its equator, the surface turns once in about 25 days. Near the poles, the rotation takes about 35 days. This difference is called differential rotation, and it matters because it stretches and winds the solar magnetic field. The result is not a simple bar magnet sitting inside a glowing ball. It is a changing magnetic system produced by moving charged material in a rotating star. Sunspots, flares, and coronal mass ejections are all linked to this magnetic activity. The Sun's spin is therefore not only a motion of its outer layers, it helps shape the space weather that reaches planets, including Earth. The rotation began before the Sun became a mature star. When gas in the solar nebula collapsed toward the centre and formed a protostar, that gas carried angular momentum, and some of it entered the young Sun. Some remained in the disk, some was carried away by outflows and magnetic interactions. Without those losses, the young Sun would likely have rotated far faster than it does now. This is a central problem in star formation. A collapsing cloud naturally spins up, but many mature stars rotate more slowly than a simple collapse calculation would predict. The missing angular momentum has not vanished, it has been redistributed through the disk, the planets, magnetic fields, stellar winds, and expelled material. Young stars often rotate rapidly because they are still contracting and still carrying a strong memory of their birth clouds. As they settle into long, stable lives, their rotation can be slowed by magnetized winds. A stellar wind is a flow of charged particles escaping from a star. When that flow is tied to magnetic field lines, it can carry angular momentum away. The effect is gradual, but over millions and billions of years it changes a star's spin. For stars like the Sun, this slowing is strong enough that rotation becomes a rough clock. Younger solar-type stars tend to spin faster, while older ones tend to spin more slowly, although the relation is affected by mass, magnetic activity, and internal structure. The general idea is called gyrochronology, meaning the use of stellar rotation to estimate age. It works best for certain kinds of stars and must be applied carefully, but it shows how deeply rotation is connected to stellar history. A star's present spin can carry evidence of its formation, its magnetic behaviour, and the time it has spent losing angular momentum into space. Rotation also shapes the interior of a star. A rotating star is not in exactly the same condition as a non-rotating one. The outward tendency associated with rotation is strongest near the equator. So very fast rotators can become flattened, with a wider equator and narrower polar regions. In extreme cases, the equator may be cooler and dimmer than the poles because the surface gravity is weaker there. This effect is observed in some rapidly rotating stars. Rotation can also stir material inside a star, mixing chemical elements between layers that would otherwise remain more separated. That mixing can affect how long the star burns fuel, how elements are brought toward the surface, and how the star evolves after its main stable phase. The changes are especially important in massive stars, whose rapid rotation can influence their winds, their final core structure, and the kind of explosion or collapse they may produce. Spin is not a cosmetic property of a star. It can alter the star's shape, its internal flow, and its future. The role of rotation becomes more complicated because a star is not always alone. Many stars are born in binary or multiple systems, where two or more stars orbit a common centre of mass. In close binaries, tides can exchange angular momentum between spin and orbit. A star may be forced to rotate at the same rate as its orbit, or material may flow from one star to another and form an accretion disk. That transferred gas carries angular momentum, so it can spin up the receiving star or compact remnant. In some systems, this process produces rapidly rotating white dwarfs, neutron stars, or black holes. A star's spin can therefore be shaped not only by its birth cloud and wind, but by the presence of a companion. The history of rotation may include mass transfer, tidal locking, merger, or common envelope evolution, where one star expands so much that both stellar cores move inside a shared outer layer. These interactions are important because many of the most energetic events in astronomy come from systems where angular momentum has been stored, exchanged, and concentrated over long periods. Even a single star changes its rotation as its structure evolves. When a Sun-like star begins to exhaust hydrogen in its core, it later expands into a red giant. Its outer layers grow enormously in radius, and those outer layers tend to rotate more slowly as they spread outward. The core, meanwhile, contracts and can rotate faster, though internal processes transport angular momentum between the core and envelope. Observations of stellar vibrations, a field called asteroseismology, have shown that the interiors of some evolved stars rotate differently from their surfaces. This gives astronomers a way to probe hidden motion inside stars that cannot be opened or sampled directly. The surface spin is only part of the story. A star may contain layers turning at different rates, connected by magnetic fields, waves, turbulence, and internal flows. Understanding that hidden exchange is one of the continuing challenges of stellar physics. The visible calm of a star in the night sky does not mean its interior is dynamically simple. The Sun itself carries this layered behavior in a gentler form. Its outer convection zone, where hot plasma rises and cooler plasma sinks, participates in the magnetic cycle. Over roughly 11 years, the number of sunspots rises and falls as the solar magnetic field reorganizes. The full magnetic cycle takes about twice that long because the field reverses polarity and then returns. Rotation helps drive this system by winding magnetic fields through differential motion. When magnetic stress builds and reconnects, energy can be released into the corona, sending radiation and charged particles outward. These events are not caused by rotation alone. They depend on plasma motion, magnetic field structure, and the Sun's internal energy. But rotation is part of the engine that organizes the field. Without it, the magnetic life of the Sun would be very different. The habitability of planets can be influenced by this activity. Stellar flares and winds can affect atmospheres, especially around small planets close to active stars. The rotation of a star therefore reaches outward into the environments of its worlds, around red dwarfs, which are smaller and cooler than the Sun. Rotation and magnetic activity can remain strong for long periods. Many red dwarfs spin down more slowly than Sun-like stars, and some produce powerful flares. Because their habitable zones lie close to the star, planets there may receive intense magnetic and particle activity. This does not automatically make such planets lifeless, but it adds a constraint. The star's spin becomes part of the planet's atmospheric history. A world can orbit at a distance where liquid water is possible by temperature alone, yet still face erosion or chemical change from stellar activity. Rotation, in this case, becomes one of the quiet links between star formation and planetary habitability. The motion inherited from a collapsing cloud may influence a magnetic field. The magnetic field may shape a wind, and the wind may affect an atmosphere. A small angular momentum remainder in a forming system can echo through many later conditions. Stars also give rotation back to the wider universe. Their winds remove angular momentum and enrich surrounding space with processed material. Their deaths can leave compact remnants whose spins record both the original star and the collapse that ended it. Supernova explosions can disturb nearby gas, seed new clouds with heavier elements, and help trigger future star formation. The next generation of stars forms from matter that has already passed through earlier cycles of rotation, magnetic activity, wind, and collapse. The process is not a closed loop in perfect balance, but it is cumulative. Angular momentum is carried, moved, lost from one object, gained by another, and stored in orbits and disks. A star's refusal to remain still is therefore not simply a result of its birth. It is part of an ongoing exchange between the star and its surroundings. The broader pattern becomes clearer at galactic scale. Stars rotate on their axes, but they also orbit within galaxies. Their individual spins are usually small compared with the enormous angular momentum of a galactic disk, yet both belong to the same accounting of motion shaped by gravity and formation. The Sun turns slowly beneath its magnetic cycle, while also travelling around the Milky Way. Every star in a galaxy carries its own local history, but together they trace a larger circulation. To understand why spin persists across the universe, the next step is to leave the surface of stars and follow their collective motion around the centres of galaxies, where gravity tries to gather matter inward and angular momentum keeps entire stellar systems spread across space. A galaxy appears still in a long exposure, but its shape is maintained by motion. The Milky Way is a broad rotating system of stars, gas, dust, and dark matter, with the Sun moving around the galactic centre rather than resting inside the disk. The journey is slow by human time and enormous by physical scale. One circuit takes hundreds of millions of years, so no human record can watch the path close. Yet the motion is measured through the velocities of stars and gas, through shifts in light, and through the structure of the disk itself. A spiral galaxy is not a solid wheel. Its stars do not attach to rigid arms and turn together like painted marks on a plate. Each star follows its own orbit through the combined gravity of the galaxy, while gas clouds collide, cool, form stars, and respond more strongly to pressure and magnetic fields. The disk remains extended because the material inside it carries angular momentum. Gravity pulls inward. But the sideways motion keeps stars and gas from falling straight toward the centre. This is the same broad conflict seen in a young stellar disk, enlarged until the centre is not a protostar and the orbiting material is not a narrow ring of dust. It is an entire galaxy. The rotation of a galaxy begins with the way matter gathers into a dark matter halo. In the early universe, dark matter forms large gravitational wells before ordinary gas can cool into luminous structure. These halos are not isolated spheres forming in perfect symmetry. They grow through mergers, infalling streams, and the tidal pull of neighbouring regions. As they grow, they acquire angular momentum from uneven gravitational torques, and from the orbital motion of material falling into them. Gas later enters these halos along filaments of the cosmic web. It does not arrive equally from every direction. It comes along preferred paths, carrying the memory of the surrounding structure. If it can cool, it settles inward. But cooling alone does not remove angular momentum. The gas cannot all collect at the centre. Instead, much of it finds a rotating configuration, spreading into a disk where stars can form. A galactic disk is therefore the visible consequence of both gravity and angular momentum acting over vast time. The ordinary matter shines, but the invisible halo helps shape the motion. This becomes especially clear in rotation curves, if most of a galaxy's mass were concentrated in its bright centre. Stars farther out would be expected to orbit much more slowly, as planets farther from the Sun generally do. In many spiral galaxies, the outer stars and gas move faster than the visible matter alone can explain. The rotation curve stays flatter than expected. This is one of the main lines of evidence for dark matter and unseen mass component extending far beyond the bright disk. The point is not merely that galaxies rotate, It is that their rotation reveals mass that cannot be accounted for by stars and gas alone. Angular motion becomes a measuring tool. By watching how quickly material orbits, astronomers infer how gravity is distributed. The spinning disk becomes a way to weigh the invisible. This does not mean every galaxy rotates in the same manner. Spiral galaxies often display clear-ordered motion, with gas and many stars sharing a disk-like circulation. Elliptical galaxies are different. They can contain stars moving on more varied orbits, with less obvious flattening and less cold gas. Some ellipticals rotate significantly, while others are supported more by random stellar motion than by a clean disk. Their histories often include mergers, where two or more galaxies pass through one another, exchange energy and angular momentum, disturb disks, and build a larger system. A merger does not destroy angular momentum, it redistributes it. Some goes into the orbit of the combined system. Some moves into tidal tails, streams, and outer halos. Some may drive gas inward toward the center, feeding star formation or a central black hole. The final galaxy may look less like a disk, but the original turning motion still exists in altered form. Even disorder has an angular momentum history. Spiral arms add another layer of caution. They look like material arms, but they are better understood as patterns in the disk, regions where gas and stars are more densely arranged for a time. Stars can move into and out of spiral arms during their orbits. Gas entering these regions can be compressed, encouraging star formation, which makes the arms bright with young stars. The arms do not require the whole disk to rotate as a solid object. In fact, galaxies rotate differentially, meaning material at different distances from the center moves with different angular speeds. This differential motion would wind any fixed material arm tightly over time, so spiral structure has to be understood as a pattern maintained by gravity, density waves, interactions, or other disk processes. Rotation creates the stage, but the visible spiral is a pattern within that stage. Bars, rings, and central structures also show how angular momentum moves inside galaxies. Many spiral galaxies have a bar crossing the center, a long concentration of stars whose gravity can redirect gas and alter orbits. A bar can help move angular momentum outward, while allowing gas to drift inward. That inward gas may build central star clusters, feed new star formation, or contribute to the growth of a supermassive black hole. The galaxy does not simply spin unchanged for billions of years. Its internal structures act as channels through which angular momentum is exchanged. The disk can spread, the center can gain mass, the outer regions can absorb motion, satellite galaxies can tug at the disk, warp it, or leave streams of stars as they are torn apart. Rotation is persistent, but it is not static. It is a long negotiation between gravity, angular momentum, cooling gas, stellar feedback, and repeated encounters. The Milky Way carries signs of this history. Its disk is not perfectly flat and simple. It has spiral structure, a central bar, a surrounding halo, streams from disrupted smaller galaxies, and a supermassive black hole at its center. The Sun travels within this system, above and below the midplane over time. While orbiting the center, its motion is part of the galaxy's overall angular momentum, but it is also influenced by local gravitational encounters, spiral structure, and the uneven mass of the disk. The solar system's galactic orbit has no daily effect that can be felt at Earth's surface, yet it places the Sun within a changing stellar environment over deep time. Nearby stars shift. Molecular clouds are encountered at great distances and rare intervals. The background of cosmic rays and interstellar material can vary. These influences are subtle compared with the Sun's direct control over Earth, but they show that galactic rotation is not an abstract fact. It is part of the long setting in which planetary systems move. Galaxies also make clear why rotation is not simply a property of objects that spin around their own axes. Much of the universe's angular momentum is orbital. Stars orbit galactic centers, gas orbits inside disks. Satellite galaxies orbit larger galaxies. Galaxy pairs orbit and merge. These motions can later become internal rotation, tidal streams, black hole accretion disks, or disturbed stellar halos. Angular momentum moves between scales. It can begin in the tidal torques of early structure, appear as a galactic disk, shift during a merger, and end partly in the spin of a central black hole or the orbit of material far outside the main galaxy. There is no single container for it. It is a conserved thread passing through changing forms. This is why a galaxy can remain spread across tens of thousands of light years instead of collapsing quickly into its center. Gravity keeps asking matter to fall inward. Angular momentum keeps forcing the answer to be more complicated. Some gas does fall inward, especially when bars, collisions, or instabilities remove angular momentum from it. Some stars are scattered into new orbits. Some material is thrown outward. A disk can thicken, warp, or be rebuilt by later infall. Over cosmic time, the galaxy becomes a record of every way angular momentum has been gained, lost locally, transferred, and preserved globally. The visible turning of the Milky Way is only one expression of that record. The deeper point is that rotation gives galaxies time. It slows collapse, spreads material, allows gas to form stars across a broad disk, and creates environments where planetary systems can arise far from crowded centers. Without angular momentum, gravity would build a much more concentrated universe, with fewer long-lived disks and less extended structure. With it, matter circulates, gathers gradually, and forms patterns that remain visible for billions of years. The next step leads to the places where this circulation is compressed almost beyond ordinary intuition, because when the angular momentum of a star or disk is forced into a tiny remnant, rotation reaches its most extreme known forms. The fastest rotation known in astronomy appears when collapse leaves almost no room for angular momentum to spread out. A massive star can live for millions of years with a core held up by pressure from nuclear fusion, while its outer layers shine steadily enough to hide the instability waiting at the end. When the central fuel is exhausted, the balance changes. Gravity no longer meets enough outward support in the core, and collapse begins. The material that once occupied a region far larger than Earth is forced inward to a size comparable to a city. If even a portion of the original angular momentum remains in that shrinking core, the rotation must accelerate. The result can be a neutron star, one of the densest known forms of matter. It is not a normal star made smaller. It is a collapsed remnant where protons and electrons have been pressed together into neutrons under extreme gravity, leaving an object with roughly the mass of the Sun packed into a sphere only about a dozen miles across. At that scale, the old rule becomes severe. A modest stellar rotation, compressed into such a small radius, can become hundreds of rotations each second. This is not a failure of common sense so much as a warning that ordinary sizes make rotation look gentle. When the size is removed, the stored angular momentum becomes unmistakable. Many neutron stars are detected as pulsars because their magnetic fields guide beams of radiation that sweep through space as the star turns. If one of those beams crosses Earth, observatories receive a pulse with each rotation. The regularity can be extraordinary. Some pulsars keep time with such stability that small changes reveal the presence of companion stars, planets, gravitational effects, or energy loss from the rotating remnant itself. The pulse is not the star blinking on and off in all directions. It is a rotating beam, more like a lighthouse in structure, though the physical cause is far more extreme. The beam is tied to magnetic fields and charged particles moving near the neutron star. Because the magnetic axis does not always align with the rotation axis, the beam sweeps across space. The observed rhythm is therefore a direct measure of spin. The fastest known pulsars rotate hundreds of times per second, with the most rapid confirmed examples completing more than 700 rotations in 1 second. The surface moves at a significant fraction of the speed of light, yet the star remains held together by gravity and nuclear physics. There is a limit to how fast it can turn. If a neutron star rotated too quickly, material at the equator would no longer remain bound, and the star could shed mass or become unstable. Rotation is powerful, but it is not unlimited. Neutron stars can also be spun up after birth. In a close binary system, a neutron star may draw gas from a companion. The gas does not fall straight onto the surface. It forms an accretion disk because it carries angular momentum. As material in the disk spirals inward, it can transfer angular momentum to the neutron star and make it rotate faster. This process can create millisecond pulsars, old neutron stars that have been recycled into extremely rapid rotation by feeding from a companion over long periods. The term recycled is useful because the star is not young in the ordinary sense. It has been altered by its environment. The original supernova left the remnant behind, but later accretion changed its spin. Here again, the same accounting appears in a different form. Angular momentum moves from orbiting gas into the compact star. The disk loses enough angular momentum to fall inward, while the neutron star gains some and spins faster. A system that might look like a dead stellar remnant becomes active again because motion is transferred across scales. Some neutron stars show another form of extreme behavior through magnetism. Magnetars are neutron stars with magnetic fields far stronger than those of ordinary pulsars. Their rotation may be slower than the fastest millisecond pulsars, but their magnetic energy is immense. Starquakes in the crust and sudden rearrangements of magnetic fields can release powerful bursts of radiation. Their spin still matters because it helps define the timing and structure of their emission. But magnetars show that angular momentum is not the only stored quantity in compact remnants. Magnetic field, internal stress, temperature, and gravity all matter. This distinction keeps the explanation careful. Fast spin is one outcome of collapse, not the whole story of every neutron star. Some are fast because they were born with high rotation. Some become fast through accretion. Some slow down as they lose rotational energy through radiation and particle winds. The important point is that a neutron star's rotation is a readable record of collapse, exchange, and loss. Over time, pulsars slow because they radiate energy and angular momentum. Their pulses lengthen. Their magnetic environments change. The spin is not frozen, but it remains governed by conservation. Black holes carry the idea farther. A black hole can form when the core of a massive star collapses beyond the point where any known pressure can halt it, or when compact objects merge, or when massive concentrations grow over time in galactic centers. Once a black hole forms, it is described from outside by mass, electric charge, and spin. Though astrophysical black holes are expected to have very little net charge. Spin is therefore one of the essential observable properties. A rotating black hole is different from a non-rotating one because it changes the geometry around it. The event horizon marks the boundary beyond which light cannot escape. But outside that boundary, a rotating black hole also produces frame dragging. Spacetime near it is dragged in the direction of rotation. In a region called the ergosphere, no object can remain still relative to distant space. Motion with the rotation becomes unavoidable. This does not mean matter is being pulled by a surface, because a black hole has no solid surface. It means rotation has become part of the structure of the surrounding spacetime. Accretion disks around black holes make this spin observable indirectly. Gas orbiting close to the black hole heats to extreme temperatures and emits X-rays. The innermost stable orbits depend on the black hole's spin. A rapidly rotating black hole allows material to orbit closer before plunging inward, which changes the radiation from the disk. Astronomers use these effects, along with the shapes of spectral lines and timing patterns, to estimate spin. The measurements are difficult and model-dependent, but they show that many black holes rotate significantly, and some may be close to the maximum allowed by general relativity. That maximum matters. A black hole cannot be spun up without limit. As spin increases, the structure of the horizon and surrounding spacetime approaches an extreme condition. Additional material can add angular momentum, but it also adds mass. Radiation can carry angular momentum away, and real accretion is limited by the physics of disks and fields. The laws do not permit a stable astrophysical black hole to exceed the boundary where the event horizon would cease to behave as required. In this sense, even the darkest compact objects obey strict accounting. Rotation becomes extreme, but it remains law-bound. The spin of a black hole can also store extractable energy. Magnetic fields anchored in surrounding plasma may draw rotational energy from the black hole and help power jets that extend far beyond the central region. These jets are seen in some active galaxies and stellar mass systems, where narrow streams of particles move outward at high speed. The details involve plasma physics, magnetic fields, accretion disks, and relativity. But the broad significance is clear. Angular momentum compressed into a black hole does not simply vanish behind the horizon from the viewpoint of the surrounding universe. It influences the environment, shapes nearby orbits, affects radiation, and may help launch material across enormous distances. Spin reaches its most severe form in compact objects, yet its consequences can be much larger than the object itself. The path from a slowly rotating cloud to a pulsar or black hole is therefore continuous in principle, even though the physical states are very different. A cloud begins with a small angular momentum remainder. A star forms after that motion is redistributed through a disk. The star lives, loses mass, exchanges angular momentum through winds or companions, and eventually collapses if it is massive enough. Collapse reduces size so drastically that any remaining angular momentum becomes concentrated. A neutron star may emerge as a rapid pulsar. A black hole may inherit spin and drag nearby spacetime. Later, accretion can spin compact objects up or down. Mergers can combine angular momentum in violent ways, sending some into gravitational waves and leaving a rotating remnant behind. At no point does rotation need to be invented anew. It is carried, transformed, intensified, and sometimes partly removed. Compact remnants show the same rule at its sharpest because they leave almost no distance, over which angular momentum can be quietly distributed. This is why the fastest spinners in the universe are not large disks or wide planets, but collapsed remains. They are the end result of gravity winning the battle over size while conservation keeps the turning motion in the account. The next question is what the universe would look like if that account could somehow be erased. Because removing rotation would not create peace. It would remove one of the main reasons cosmic structures survive in recognizable form. Removing rotation from the universe sounds, at first, like removing motion from a machine so it can finally rest. In physics, it would do almost the opposite. Rotation is not a decorative feature placed on top of planets, stars, and galaxies. It is one of the ways those systems remain extended, balanced, and able to change slowly instead of collapsing all at once. A useful thought experiment can begin with Earth, but it has to be stated carefully. Nothing in known physics can simply stop Earth's rotation without transferring angular momentum somewhere else. A force strong enough to halt the planet would have consequences of its own. Still, imagining the rotation suddenly removed shows how much of ordinary planetary order depends on the turning that usually goes unnoticed. The solid surface would no longer move eastward with the same speed it now has, while the atmosphere and oceans would tend to continue moving because of inertia, air near the equator, formerly sharing Earth's rotation, would sweep across the surface at enormous speed. Oceans would surge, coastlines would be overwhelmed, and the crust itself would be stressed by the change. The event would not feel like quiet stillness. It would feel like the sudden disagreement between layers of a planet that had always moved together. After the first violence, a slower reshaping would follow. Earth is not a perfect sphere. Its rotation helps make it slightly wider at the equator than from pole to pole. This equatorial bulge affects the shape of sea level and the distribution of water. Without rotation, the planet would gradually adjust toward a different equilibrium. Oceans would no longer be held outward in the same way near the equator, and water would tend to redistribute toward lower gravitational potential, with major changes in global sea level. The exact geography would depend on the uneven shape of continents and ocean basins, but the present map would not survive. Day and night would also change completely. If Earth kept orbiting the Sun but no longer rotated relative to distant space, a full cycle of sunlight would be tied to the year rather than to the day. One side would face the Sun for a long season, then turn away only through the planet's orbital motion. Weather patterns, temperature gradients, winds, evaporation, ice, and biology would all be forced into a new and severe arrangement. The familiar 24-hour rhythm is not a small environmental detail. It is a central condition for the climate and for the life that evolved within it. Other planets would suffer in different ways. A world with no axial rotation can still orbit a star, but the absence of a daily cycle changes how heat moves through its atmosphere and surface. The side receiving prolonged sunlight can grow much hotter, while the dark side can cool deeply unless an atmosphere or ocean transports heat efficiently. Some planets around small stars may become tidally locked, with one hemisphere facing the star for long periods, and such worlds are studied as possible stable environments under the right conditions. But that is not the same as removing rotation suddenly from a planet designed by its history to have it. A planet's atmosphere, magnetic field, internal circulation, and surface climate develop together with its rotation rate. Change that rate sharply, and the rest of the system cannot remain unchanged. Rotation helps organize winds through the Coriolis effect, which deflects moving air and water in a rotating frame. Without it, the circulation of atmospheres and oceans would be rebuilt from the ground up. The loss of planetary spin would also affect magnetic fields in some worlds. Earth's magnetic field is generated by motion in its liquid outer core, and rotation helps organize the flow into a large-scale dynamo. The field is not produced by rotation alone. It depends on heat, convection, electrical conductivity, and the structure of the core. But if rotation were removed or greatly altered, the dynamo could weaken, reorganize, or fail depending on the planet. A weaker magnetic field would change how the solar wind interacts with the upper atmosphere. Over long periods, that can influence atmospheric escape and radiation conditions near the surface. Again, the point is not that every magnetic field instantly disappears when spin changes. The point is that rotation is part of the working structure of a planet. It links the deep interior to the atmosphere and to space. Remove it, and the whole chain must adjust. Around stars, the consequences become larger and less intuitive. A star without rotation would still be held by gravity and internal pressure, and it could still shine if nuclear fusion continued in its core. But real stars use rotation as part of their magnetic and structural lives. In sun-like stars, Differential rotation helps wind magnetic fields and contributes to activity cycles. In rapidly rotating massive stars, spin can change the star's shape, drive mixing between layers, influence mass loss, and affect the final core that later collapses. Removing that rotation would not simply produce a calmer version of the same star, it would alter internal transport, magnetic behavior, and long-term evolution. For stars in close binaries, where spin and orbit are tied by tides or mass transfer, erasing spin would disturb the exchange of angular momentum that controls the system's future. Some accretion disks would lose the very property that allows them to exist as disks. Gas with angular momentum circles and gradually moves inward as that angular momentum is redistributed. Gas with none would fall much more directly, changing the rate, brightness, and structure of accretion. Compact objects make the thought experiment even more severe. A neutron star can store enormous rotational energy. If its spin were removed, that energy and angular momentum would have to go somewhere, perhaps into radiation. Particles, gravitational waves, or the motion of surrounding matter, depending on the imagined process. A black hole's spin is part of the geometry outside it. Removing it would change the event horizon, the ergosphere, nearby orbits, and the energy available to surrounding magnetic fields and jets. Such a change cannot be treated as a simple breaking of a solid object, because the object is space-time and gravity in an extreme state. The lesson is the same as before, only sharper. Spin is not an accessory. It is part of the physical identity of the system. At galactic scale, removing rotation would threaten the structure itself. A spiral galaxy remains broad because its stars and gas have orbital angular momentum around the center. They are not supported by pressure in the way gas in a balloon is supported. They follow paths shaped by gravity and sideways motion. If that angular momentum were erased, stars and gas would no longer have the same reason to remain spread across the disk. Matter would begin moving on far more radial paths toward the center and through one another's orbits. Gas clouds would collide, heat, lose energy, and fall inward more efficiently. Star formation could be compressed into dense regions. A central black hole could receive more material. The graceful disk would not remain a disk. It would become a much more concentrated and unstable system. The exact outcome would depend on how the angular momentum was removed and how the mass was distributed, but the broad point is secure. Galactic rotation is one of the main reasons galaxies do not quickly become only dense central concentrations. It gives matter time and space to form stars across wide regions. Clusters and larger structures would also change if orbital angular momentum disappeared. Galaxies moving inside groups and clusters carry angular momentum in their paths around shared centers of mass. Mergers, tidal streams, halo shapes, and the long survival of satellite systems all depend on those motions. Remove them, and the history of structure formation would be rewritten. The universe would become more directly collapsing, less disk-shaped, and less able to preserve extended systems over billions of years. But this is why the thought experiment reaches its limit. Angular momentum cannot simply be erased from everywhere. To stop one object spinning, another object, field, wave, or flow must receive what was removed. Breaks heat, tides transfer spin into orbit. Magnetic winds carry angular momentum outward. Gravitational waves can remove it from merging compact objects. There is always a destination. A universe in which all rotation vanished at once would not be a possible continuation of the same laws. It would require the failure of one of the principles that connects motion to the symmetry of space itself. The usefulness of the question is therefore not that it predicts a real future. It reveals what rotation is already doing. It keeps planets cycling through light and darkness. It helps organize atmospheres, oceans, interiors, and magnetic fields. It shapes stars and their activity. It spreads galaxies into disks and delays collapse. It stores energy in compact remnants and influences the space around black holes. Stillness, imagined at cosmic scale, is not peaceful. It is the removal of a stabilizing condition. The universe remains recognizable because matter does not merely fall inward, it turns, orbits, exchanges, and carries angular momentum forward. The final step is to return from this impossible stillness to the real cosmos, where no master spin is required, and where countless local rotations continue because small motions, once caught by gravity, are very difficult to erase. The universe does not need to spin as one object in order to fill itself with rotation. That is the central answer left after following the motion from Earth to galaxies and down into matter. The largest observable scale shows no confirmed master turn, no shared axle for all space, and no evidence that the Big Bang was a rotating explosion into surrounding emptiness. Space expanded from an early hot, dense state, and within that expansion small, uneven regions began to grow. Matter moved. Gravity gathered it, and perfect cancellation almost never occurred inside the clouds and halos that later became stars and galaxies. The strange reason so much in space spins is therefore not one dramatic beginning. It is the combination of small sideways motions, gravitational collapse, and the conservation of angular momentum. Each part is simple enough to state. Matter rarely begins with no motion at all. Gravity pulls matter inward. Angular momentum cannot simply disappear. When these conditions act together, rotation becomes hard to avoid. A cloud that barely turns can become a disk. A disk can make a star and planets. A star can leave behind a compact remnant that spins rapidly. A galaxy can remain broad because its stars and gas move around the center instead of falling straight in. The same accounting does not make every system identical, but it gives them a shared physical grammar. The motion may be slow and spread across light years, or fast and compressed into the space around a neutron star. In both cases, the system carries angular momentum that has to be conserved, transferred, or carried away. This also explains why space contains order without complete uniformity. Many planetary systems form from disks, so their planets often share a broad orbital plane. Many galaxies form rotating structures, so stars and gas can circulate for billions of years, but the directions are not all the same, because the first angular momentum in each region came from local conditions. One cloud was pulled by one set of neighbours, another grew along a different filament of the cosmic web. A young planet was struck by one sequence of impacts, while another was tilted or slowed by a different set of encounters. Tides changed some rotations, magnetic winds slowed some stars, mergers reshaped some galaxies. The result is not a universe moving in military alignment. It is a universe in which the same law acts through many histories. Venus can rotate backward while the solar system still preserves the disk pattern. Uranus can lie on its side while the major planets still orbit in a shared direction. A spiral galaxy can be flattened by rotation, while an elliptical galaxy stores more of its motion in varied stellar paths. Exceptions are not failures of the law. They are records of later transfers. Angular momentum remains present, but the form it takes depends on what has happened to the system. The most useful way to think about rotation is as a record of formation. A planet's day remembers the disk, the impacts, and the tides that shaped it. A star's spin remembers the collapsing cloud, the magnetic wind, and any companion that exchanged matter or torque with it. A galaxy's rotation remembers the early dark matter halo, the infalling gas, the mergers, and the long movement of material through its disk. A neutron star's rapid pulse remembers the collapse of a massive core and, in some cases, the later transfer of gas from a companion star. Even a black hole's spin carries information about the matter and compact objects that built it. None of these memories is perfect. The original motion is edited by time. Still, rotation leaves a kind of physical continuity. It connects an object's present behavior to conditions that may no longer be visible. The disk may be gone, but the planets continue to orbit. The birth cloud may be dispersed, but the star still turns. The merger may be ancient, but a galaxy's halo and streams may still show how angular momentum was redistributed. Motion becomes evidence. This is why the search for spin is also a search for history. Astronomers measure the rotation of planets by watching surface features, clouds, magnetic fields, or repeated signals. They measure stellar rotation through changes in brightness, spectral line broadening, magnetic activity, and star spots carried across a surface. They measure galactic rotation through the Doppler shifts of stars and gas, where light becomes slightly redder or bluer depending on motion toward or away from the observer. They measure black hole spin indirectly through the behavior of hot gas close to the event horizon and through relativistic effects in accretion disks. Each measurement asks a related question. How is angular momentum distributed here? What has carried it inward or outward? What has slowed the system? What has spun it up? The answer often reveals more than speed. It reveals mass, structure, age, magnetic behavior, hidden companions, dark matter, or the past presence of collisions. Rotation is not only something objects do, it is one of the main clues to how they became what they are. There is a further caution. The statement that everything spins is useful only if it is handled with care. Not every object rotates in the same way. A planet spinning on its axis is different from a planet orbiting a star. A star rotating as plasma is different from a rigid body turning as one piece. A galaxy is not a solid wheel. An electron spin is not a tiny version of Earth's rotation. Some systems are dominated by ordered rotation, while others are dominated by random motion, turbulence, or pressure. But angular momentum appears across all of these descriptions, and that is the real connection. The universe uses angular momentum as one of its basic conserved quantities. It shows up in orbits, disks, magnetic fields, quantum states, compact remnants, and the circulation of galaxies. The forms differ because the scales and rules differ. The continuity lies in the accounting, not in a single picture that can be stretched from electrons to galaxies without change. What would be truly strange is not that the universe contains so much spin. It would be stranger if it did not. A universe with matter, gravity, and motion would have to be arranged with impossible precision to prevent local angular momentum from appearing. Every collapsing cloud would need all sideways motions to cancel exactly. Every surrounding tidal pull would need to line up in perfect symmetry. Every collision would need to remove rather than redistribute spin. Every disk would need to give away its angular momentum without leaving planets, moons, jets, winds, or outer reservoirs. Real structure formation is not that exact. It is uneven, interactive, and cumulative. Small differences grow, motions are exchanged. Collapse compresses what remains. The universe turns because perfect stillness is not the default outcome of matter under gravity. It is the exceptional condition, and the cosmos does not generally supply the level of symmetry that exception would require. The deeper reason is tied to symmetry itself. Conservation laws arise because the laws of physics have stable patterns. Angular momentum is conserved because space has rotational symmetry, meaning the basic laws do not depend on choosing one particular direction as special. A closed system can be turned in orientation without changing the laws that govern it, And from that symmetry comes the conservation of angular momentum. This connection is more abstract than the motion of planets, but it gives the whole subject a firmer base. Spin persists not because nature prefers circles as a visual shape, but because the laws of motion preserve angular momentum when no outside influence removes it. Gravity can gather matter. Collisions can redistribute motion. Magnetic fields can carry it away. Tides can transfer it from spin into orbit, but the total account must still be settled. This makes rotation one of the most reliable threads through a changing universe. In the end, the calmest answer is also the most complete one. Everything in space seems to spin because the universe began with matter in motion, because gravity made small imbalances important, and because angular momentum is conserved as structures shrink, collide, orbit, and evolve. Earth's turning day, the moon's locked face, the sun's magnetic cycle, the flatness of planetary systems, the broad disks of galaxies, the pulses of neutron stars, and the dragged space-time around rotating black holes are separate expressions of that same rule working in different environments. No single cosmic wheel is required. No hidden engine has to keep the motion going. The universe is not spinning as one whole, but within it, local systems keep inheriting, concentrating, sharing, and preserving angular momentum. The result is a cosmos where stillness exists only in chosen frames of reference, while deeper motion continues almost everywhere. Rotation is not an accident added after structure forms. It is part of the way structure becomes possible, part of the way gravity avoids immediate collapse, and part of the evidence that the present universe still carries the motions of its beginning in every turning world and every circling star. The motion remains, quiet beneath every scale. Earth keeps turning beneath its atmosphere. The moon keeps its steady face toward the planet. The sun rotates through its magnetic cycle, losing a little angular momentum into space as charged particles drift outward. Far beyond it, stars continue their long paths around the Milky Way, and the galaxy itself keeps its broad disk open against the inward pull of gravity. None of this requires a single cosmic axis or a hidden wheel behind the universe. It follows from matter that began with motion, from gravity that gathered that matter into structure, and from a conservation law that does not allow turning motion to vanish without being carried somewhere else. In that sense, spin is not a strange exception to stillness. Stillness is the narrower idea, useful only within a chosen frame. The wider universe is made of shared motions, inherited motions, altered motions, and motions too small or too slow to feel. Some rotations become days. Some become orbits. Some become magnetic cycles, accretion disks, pulses from collapsed stars, or the measured curve of a galaxy that reveals matter no telescope can see directly. The same principle appears again and again, never as a perfect repetition, always shaped by the history of the system carrying it. A cloud collapses, a disk forms, a planet is struck and tilted, a star slows through its wind. A black hole keeps the spin of what built it. The universe is not a dance in the poetic sense so much as a continuing account, balanced through gravity, motion, and time. What remains is a calm recognition. Every turning world is not only moving now, but preserving part of an older motion, passed forward from the earliest unevenness into the structures that still surround it.